Hello, this is the Thursday session for the Love Data Week, the Thursday afternoon session. And our first speaker is myself, and I'll be presenting CSO data flagging. And I'll begin now. Sorry there. So hello, my name is Conor, and today I'll be walking you through some of the work I've completed on automating sensitive data detection while working in the CSO during a 3-month placement. So we can start off by explaining who the CSO are. They're the Central Statistics Office, and you most likely know them for collecting census data last year. They were founded in 1949, and their head office is in Cork. They're responsible for gathering information relating to economic, social, and gender activities and conditions in Ireland. Most importantly, for this talk, they're responsible for ensuring statistical confidentiality, where data gathered can only be used for statistical analysis. So I worked at the CSO on placement in the Administrative Data Centre, or ADC for short. The ADC compile information from other government departments, such as the Revenue Commissioners. This data is strictly confidential, and key identifiers such as PPSNs and air codes are pseudonymized to maintain this. So data within the CSO or in the ADC can be split into 3 distinct categories. The first category is the migration tier, which contains data just received from other government departments. This data is then converted into SAS file format, which is called source tier. Only trusted senior members of the ADC have access to source tier data. Once the key identifiers of source tier data are pseudonymized, the data can be moved to the analysis tier, where trusted members of the ADC can analyze the data. The problem lies with the pseudonymizing process, where columns containing personal data are encrypted with a protected identifier key, or PIK for short. In this example, we have 2 tables. The first one has a set of air codes and their corresponding favorite places in East Cork, while the other has a set of air codes and private medical information. Moving from the source tier to analysis tier, the air codes are encrypted, which we can see here. They're now PIK air codes. This makes it extremely difficult to relate information in the tables back to a specific person or household. If, however, an air code is left, let's say here, it can cause problems later on, as using the same PIK process, 2 tables can be combined, as can be seen here. And using these 2 tables in the analysis tier, we can see that this air code has still remained, as it was in a completely different column. And now we know that the person with this air code is unhealthy, which is private medical information, which should not be available. So real data tends to be extremely messy, where both personal and erroneous data appear in places they shouldn't. After the pseudonymization process, a trusted senior member of the ADC must manually sift through the data to remove any remaining sensitive or erroneous data. My goal was to try to create a program to automate some of this process, to make the manual job of sifting through columns easier. So in this example, we can see the personal data here with the phone number and air code. So that would be data that could relate back to a person. While erroneous data is just data we don't really want in a column. It's not going to be any use for analysis, and it could maybe cause problems further down the line. So the first tier, or the first step in automating the process of determining what each column expects is getting what each column expects as an input. So using a sample of a column's entries, it is possible to gauge what a column expects from an entry. Shared traits of entries can be shared as column properties, such as expected text patterns using RegEx, numerical attributes, and a list of expected classes. In the table below, we can see that the postcode column, there are many forms of air codes present. This table can then infer that the postcodes column expects air codes as an input. What is using RegEx? So what is RegEx? Well, RegEx stands for regular expressions and can be used to find patterns in data, such as with PPSNs and etc. In the example below, we can see that for PPSNs, the program looks for 7 digits, which the D stands for digits, and then the 7 here stands for 7 of them, and then 2 alphabetic characters. So between A to Z, it will accept 1 or 2. And just for the rest of this presentation, while working on the program, we decided to make all RegEx case insensitive. So columns can contain many other properties, such as classes. In this context, a class, classes are a set of expected values a column is supposed to have. This is visible in the module code column, where 4 recurring module codes are saved. Entries that are not one of these 4 classes would be flagged by the program, but this will be discussed later in further detail. Columns will also record the expected length of its text entries, known as string lengths. In the module code column, string lengths 6 and 7 are the only expected lengths. Anything else would be flagged. If the string length varies too much and cannot be recorded with a number of lengths among its entries, then the program will instead record the mean and standard deviation of string lengths, such as in the module name column. Columns also record if the entry is expected to be numeric. In this case, the mean and standard deviation of the numerical values sampled from the column are recorded. These values are recorded for the module rating column, as can be seen on the table. Some columns can contain patterns that are unknown to the program, unlike expected key identifiers, such as PPSN and mobile numbers. AI-generated RegEx can be created to detect these entries. So the process of using AI-generated RegEx only begins if the length of strings is not too varied and the column recorded a list of string lengths. To generate RegEx from these types of columns, a sample of entries will be analyzed by the program. So a different RegEx is generated for each different string length. This can be seen by the 2 tables on the right, where the top table records RegEx as string lengths of 5, and the bottom table records RegEx as string lengths of 4. Each character of a string is looped through. If the examined character is numeric, then it is recorded as such with a 0 to 9. If it is alphabetic, then it's recorded as an A to Z here. All other characters are recorded as a wildcard, which is just a full stop. This can stand for any character. The frequency of each generated RegEx is also recorded, as seen on the column to the right. Any frequency that is not of a high enough frequency is, any RegEx that is not of a high enough frequency is ignored. So for instance, this hello here, the RegEx for it is only recorded once, so the program will ignore it when trying to generate RegEx. When multiple different RegEx are generated for the same string length, they are combined into one singular RegEx. This is done by comparing each individual RegEx symbol for a particular string length. So as we can see, we have these 2 sets of RegEx strings with conflicting data here. And if this data is conflicting, so a 0 to 9 and A to Z, then this will be this character will be replaced by a wildcard in the program, while all other characters will remain. And still, any frequency that is not high enough will continue to be ignored and will not be included in the combining process. So detecting expected sensitive information can cause a lot of false positives, and this needs to be minimized. To do this, if a column contains just, for example, PPSNs, then the program will record this and not flag all PPSN entries in a column as sensitive data to the user, but instead flag all non-PPSN-like entries to the user. However, sometimes columns can contain sensitive data, but not in pure form. It is important for the program to note what types of data are expected to be present some of the time, and it is not an issue for them to appear in that column. This is done by getting a sample of entries from all columns and checking what known and AI-generated RegEx are present in within a large portion of sample entries. These RegEx patterns can then be ignored for the column entries. Finally, we can use a UML class diagram to visualize all the properties that are recorded for every column. In red, we have what particular type of known RegEx a column contains, if any. In orange, we have a list of known and AI-generated RegExes that can appear in that column. In yellow, we have a simple Boolean, a true or false value, whether or not the number is, or if the value is numeric or not. In light and dark green, we have the string length mean and string length standard deviation for the columns. Now, once again, if the column expects numeric entries, these will actually record the mean and standard deviation of numerical values in the column. And in light blue, we have a list of expected classes that can appear in the column. So in dark blue, we have a list of string lengths, which are only recorded if the lengths are not too varied in the strings of a column. And we also have a list of AI-generated RegEx that can match to entries in the column. So using these column properties, we can detect entries that do not belong to a particular column. Here's an example of column properties being useful for detecting erroneous data. For instance, banana and coconut shake has an unusual length and is not a known class, so therefore it would be flagged to the program. Hello world here is not numeric when it should be numeric in the age column. The age 82 here is too many standard deviations away from the mean. And this goes to show that the program can have faults in places, as 82 would be an acceptable age, but the program would still flag it because the sample of ages present are just not varied enough. And hello here in the mysterious data type column, it is not of an expected regex, so it would also be flagged to the user. So sensitive information is usually found by comparing entries to both known and AI-generated regex. In this example, regex is generated from the mysterious data type column and is set as a column property. During the detection phase, the program will notice that the value 12BD in the favorite food column matches the generated regex of mysterious data type column. The program will then flag 12BD as it could be sensitive information. As previously mentioned, if the favorite food column contained a reasonable number of values for the mysterious data type column, then this entry would not be flagged. Moving on, NLP was a useful tool for detecting erroneous information. It stands for natural language processing. The Enchant Python library can be used to detect words and sentences in entries. It allowed for multiple languages to be used simultaneously, such as both English and Irish. So the presence of too many words in a data entry tended to indicate that erroneous data was present in the form of a sentence. A chain of too many adjacent words, also indicated that a sentence would be present in the data entry. Words that were numeric or contained commas did not count as words to the algorithm. This helped reduce the number of false positive entries that addresses produced, as some addresses could nearly appear like a sentence. So for example here, 227 is not recorded as a single word or a chain of words because it's numeric and contains a comma, while banjo minute are a chain of words, university with the comma is not. Trampoline and county are a chain of words. Breakfast is not because of the comma. Kildare is not because it will only recognize if it will only recognize as a word if there's a capital K at the start. Mike will appear as a single word. Tyson will not due to the comma. Ireland will, so it accepts full stops, and then fake words like kachow do not. The same is similar here with an Irish example. So 305, it's numeric. It will not appear as a word. Hello will appear as a single word. World will not due to the comma. It's even Lombard, Aaron, will appear as a chain of words. Look will not due to the comma again. Neither will Olus. And Ulskull Ma will appear as a chain of words, while nude won't due to it being a single word. And may will, as it's a word in Irish, and nude won't again due to the comma. Kunde Kildara will as a chain of words. Slán won't due to the comma. And finally, Era will. Yeah, so here's an example of a rather small data set, but with sensitive and erroneous data sprinkled throughout, which the program would flag. So for instance, here in the names column, we have CJYC, which would appear as an unusual string length. As they're shorter than the average names in the name column. In the age column, we have hello world and voulez-vous fauter avec moi ce soir, which would appear as non-numeric as their alphabetic entries. And then again, we'd have the age 82 and 36 appear as an unusual numeric value due to them being too many standard deviations away from the mean. So in the mysterious data type column, we have an expected regex that should appear throughout this column, but smiling does not adhere to that, so it would be flagged to the user. And then in the favorite food column, we have multiple entries here, such as mushrooms, null, banana and coconut shake, 12BD, chicken wings, and green VD, which would appear as an unusual class. As the class it's accepting only seems to be burger and pizza in this instance. We would have chicken wings and banana and coconut shake appear as an unusual string length. Banana and coconut shake would also trigger the too many words and a chain of words flags as well. And 12BD would trigger the regex from another column, as it realizes that 12BD is an entry that would be expected over here in the mysterious data type column. And then onto the last column, we have asterisk hyphen hyphen asterisk on the lake, which would be a chain of words. No surname given would also appear as a chain of words. And Tá Cusk Kaihov Tobacco and Turvy Shaw would appear as a chain of words as well. We would have that entry also appears too many words, while we'd have and as an unusual string length as well. And then we would also have 77 or H. It would be regex from another column relating back to mysterious data type again. Now, in this instance, you can see that there's two Conors in this table, and the program will correctly not flag this as it's acceptable. But there are some instances where it should flag something that's obviously erroneous, but it doesn't. For instance, here at the asterisk hyphen hyphen asterisk, there should probably be another entry here, which will detect as unusual entry or some sort of instance like that. But this program doesn't. That could probably be completed with future work. So running this program on larger data sets could take a long time. So it was important to optimize performance. This was done with the help of multiprocessing, which could spread the computational load across multiple logical processors. This meant data sets were split into different chunks, while each logical processor worked on them separately. So to know what a logical processor is, we need to briefly look at computer architecture. Computers contain CPUs, which do most of their calculations. Modern CPUs consist of multiple physical cores to allow computing tasks in parallel. There is a process called hyperthreading, which allows these CPU cores to run multiple threads simultaneously. These threads are called logical processors and are not physical objects. Currently, it is common for each CPU core to have 2 logical processors. Modern CPUs contain 8 cores and 16 logical processors. The CSO had access to a computer with an Intel Xeon W2195 CPU, which had an astounding 18 cores and 36 logical processors. The model, this made parallelization process extremely efficient. It is important to remember, though, while using parallel computing to decrease the runtime of the program, the computing that will be done in parallel must be more computationally costly than actually copying the data from the main thread to a different logical processor and results back to the main thread again. So for the results now, the program was run on a synthetic data set containing 10,000 rows with sensitive and erroneous data placed within. The flagging results it produced were impressive, with 67 true positives, 10 false negatives, 0 false positives, and 69,878 true negatives, sorry. So while the results from running the program on synthetic data sets were impressive, running the program on a real data set produced a lot more false positives, but it still had a reasonable level of accuracy. 2 ways of improving the program further would be forcing end-of-line characters to break word chains, which would stop some addresses from being flagged as erroneous data, and preventing non-type values such as NA or null or that type of data from being incorporated into the sample data that's used to gather column properties. So finally, I'd like to thank everyone for listening to my presentation. I'd also like to thank my supervisor, Paul Rockley, for his help throughout the project. If anyone has any questions, I'd be happy to answer them. And finally, I like to end my presentations off with a bit of a slogan. So, detecting sensitive information to pseudonymize the nation. Yeah, thank you.
Hi, Conor. Can you hear me?
Hi, Cormac. Yeah, I can hear you, Cormac. Yeah.
I actually have 2 questions, if that's okay.
Yeah.
Okay. The first is, does it tend to be a big problem with erroneous data in Ireland?
Oh, like in Irish?
Well, no, in Irish. Yes, sorry. Yes.
Oh, yeah. So in Irish, there doesn't tend to be that big of a problem with erroneous data, but we have added it so the program can detect words and sentences in Irish. because I guess there is a few people living in the Gaeltacht, but they're not bad offenders for entering erroneous data into places they shouldn't be. If that answers your question, Corey.
Oh yeah, okay, thanks, it does. And my second was, what are the main issues? What were the main issues you had when you were testing a program on a real data set?
Oh yeah, so the main issues when testing the program on the real data set. So addresses really produced a big problem, because most addresses were good, but you'd have a large section of addresses which would all be a similar form of address, but it would nearly appear like a sentence. Now, I can't say exactly what addresses did appear, but it would nearly look like a sentence. Then you could maybe get 200 or 300 of these flagged up, all containing just the one address. So with here, if let's say there was commas here, it would help break up a few of the addresses, while sadly the end of line characters, I wasn't able to incorporate it into actually breaking up word chains. We did try using the \n. Where is it? Yeah, we did try using the \n to break up word chains, but it was actually a different character that they came in the form of. So it would take more work to figure that one out.
Thank you so much.
Are there any more questions there at the moment?
Yeah, Conor, we have one question in the chat.
Oh, yeah.
So Bernie is just wondering, well, she says, first of all, well done and brilliant work. She also says, you've probably explained this already, but how did it know that ka-chow could be ignored?
So for this instance, it uses the enchant library. And the enchant Python library, it's basically a dictionary, and it can contain English and Irish dictionaries. You can put whatever language of dictionary you want in it. And it will recognize that ka-chow is not a word in the English dictionary, so it will just ignore it. Or in the Irish dictionary in this case, it'll check both.
Oh, fantastic. So can you add other scripts in? So could you add like Japanese and Arabic for it to read as well?
Yeah, you can even make a custom language if you really wanted to, but it would be a big chunk of work. But adding existing languages is fairly simple. It's just download a script online somewhere, or not a script, basically a set of words that appear in a language, and you just pop it into the program that should run.
Fantastic, thank you.
Is that all the questions now?
That looks like that's it.
I think so, yeah. So I'll just end sharing my screen there now. If I can, here we are. Okay, yeah, so I'll just introduce the next speaker now. Oh, sorry. Sorry, there's a problem with my computer. There we are, okay. Yeah, so our next speaker is Yong Chen, or YC, and she's doing Bayesian Additive Regression Trees for non-ignorable missing data.
Hi, thanks, Conor. Thanks for the talk as well. That was really interesting. So can you see my screen?
Yeah, that looks great.
Yeah, okay, perfect. So I guess I'll just start. So yes, like Conor said, I'm going to talk about Bayesian additive regression trees for non-ignorable missing data today. I'm a PhD student at the Hamilton Institute, and my PhD is funded by the SFI. And my supervisors are Andrew and Keith. So, so before I talk about like what I'm actually working on, I guess this is the motivation behind the work. So we have this data set that has 5 responses and 46 predictors. Altogether, it has over 2,000 observations, but only 217 of them are complete. So this is what the response variables look like. These are the 5 responses, and they have many missing values in them. So the predictors are fully observed. Here on the right, we have the missing data pattern. So for example, this top row here, 217 cases are fully observed, and there are 8 cases where none of the responses are available at all. So when we get this sort of data set, like what do? I guess you can use like mean imputation, multiple imputation, and so on. But before I talk about our solution to this, I'll first talk about missing data. And so more specifically, I will be talking about missing data mechanisms. So the first one is missing completely at random. That's where the probability of your data being missing doesn't depend on the data itself. So here M is the missing data indicator. So if M equals to 0, then your data is missing. If M equals to 1, then your data is present. So missing completely at random is where this M here only depends on some parameters, but not the data itself. Here's a very silly example. Let's say we're modeling height versus age. So age is our predictor and height is the response. And let's say that the age is fully observed. So we know the ages of all these Simpsons characters. If the data is missing completely at random, that means the height measurements are just missing randomly, like it doesn't depend on the age or the height itself. And the next one is missing at random. That's where the probability of being missing depends on our observed data. So again, with this example, let's say that the height is more likely to be missing if you are younger. So it would look something like this. And then the last one is missing not at random. That's where our probability of being missing depends on the missing data itself. So again, with this example, that would be like if your height measurement is more likely to be missing the taller you are. So it looks something like this. Like let's say because Marge's hair is too tall that it's gone off the scales and you can't actually get a measurement for a height, and that's why it's missing. So especially when data are missing in this way, it's quite important to include the fact that it's missing and not just ignore it. Because if say you used mean imputation for this data set and you use the mean height for the observed data would be much lower than the actual data, if that makes sense. Okay, so there are two different ways of like jointly modeling our data and the missing data indicator. That is the selection model and the pattern mixture model. And so what we're using in our model or our models is basically the selection model. So here you factorize your joint likelihood, so the data and the missing data indicator in this way. So the first part is just your data distribution. So it's however you want to model your data. It could be a linear regression, could be a logistic regression, and so on. And then the second part is how you want to model your missing data indicator, and that's conditional on the data itself. So I will talk about that first. So what we're using is something called PROBIT regression. So here you have the probability of data being observed is conditional on our fully observed predictors and our response variables. And that's modeled with a standard CDF function. And so the reason why we chose a PROBIT regression is because if you just introduce some latent variables here, you can then implement a Gibbs sampler and get posterior samples quite easily. So compared to like a logit model, for example, where you would have to use Metropolis Hastings instead. Right, so just to link this function here back to the missing data mechanisms that I was talking about earlier, if we expand this set transpose beta, we get something like this, like a linear relationship. So again, X is fully observed, Y has missing values in them. So let's say beta 2 and beta 3 are both 0, then our missing data or the missingness probability only depends on this parameter beta 1. And so you would have a missing completely at random scenario. If beta 3 only is 0, then the missing probability depends on your fully observed data set, your X. So that's missing at random. But if beta 3 is non-zero, then your missing probability also depends on the missing data itself. So you would have missing not at random. So the next part that I'm going to talk about is how we model the data. So we do that using something called Bayesian Additive Regression Trees, or also BART for short, if you haven't already noticed the Simpsons scene. So BART was developed by these three guys. It's basically formed of a bunch of binary decision trees. It's a sum of trees model. So each tree acts as a weak learner for the overall model. And BART also uses regularization priors to keep each tree small and short to prevent overfitting. So this is what the MATS notation looks like for the BART model. So your data Y is normally distributed with the mean equal to the sum of trees, and tau is a precision parameter. And these are your priors. So the first one is the priors for the trees. D is the depth of the tree. So basically, you assign less probability to deeper or longer trees because you want to keep them small. Mu here is the terminal node parameter, and I'll say a little bit more about that in a bit. And then tau has a gamma prior. So basically, in a BART model, you would have binary decision trees. And if, say, you had a data that looked like this, where Y is your response, and you've got these 4 predictors, and then you've got 2 trees. In the first tree, you would have a bunch of splitting rules. And what the trees basically do is that they filter your data into these terminal nodes here. And the terminal nodes are assigned this parameter mu to them. And so if an observation falls in a certain terminal node, it would be assigned this parameter mu. So for example, Y1 falls into this terminal node in the first tree and this terminal node in the second tree. And then the mean of Y1 would be the sum of these 2 mu's. Okay, so just to recap, we talked about the data set that we have. So this is the type of data set that we want to work with. It's a multivariate data set with missing values in the response. We're working with a selection model. And we talked about the BART model and also the PROBIT regression model. So the first model that we have is basically a multivariate version of the BART model and a multivariate version of PROBIT regression. And this is what it looks like. So here, Y is a p-dimensional vector. Omega is our precision matrix. And similarly, our M is a p-dimensional vector as well. B is our matrix of parameters. So from before we had beta 1, beta 2, beta 3, but now instead it's a matrix of betas. And then R is a correlation matrix. So to implement this model, basically, we did everything in R, and we can get posterior samples of our terminal node parameters, the precision matrix, this matrix D, and also the correlation matrix via Gibbs sampling. And we can also conveniently impute our missing data using a Gibbs sampler as well. So just to show you a simulated data example. So I simulated a bivariate data set with some predictors, and then I made some of the response variables go missing on purpose and gave it to the model, and then tried to get predictions for the observed and the missing data. So here on the x-axis, we have the actual simulated data, and on the y-axis, we have the predicted values for both the observed and missing data. So if the model did well, then all these points would lie on this diagonal line here. This diagonal line is the x equals to y line. And so we can see from this example itself, it's done pretty well because everything's lying quite closely to the diagonal line. And then if we just compare this really quickly with like the BART package in R, we can see that just using the BART package, you can't get imputations for the missing values. You can only run it on the observed values. So that's already a plus for our model. And so I also ran this on that data set that I showed you before, the real data example. And this is roughly what it looks like for the 5 response variables. These are the histograms of the predicted values for the observed and missing data. So what we're trying to see here is if the missing data is or has a slightly different distribution to the observed data. So we can see like this is roughly the yellow line here is the mean of the missing data, and the black line is roughly the mean of the observed data. So if they lie far away from each other, then we could potentially conclude that, you know, the missing data is from a slightly different distribution to the observed data. And so the joint model is useful. And these are the intervals for the posterior samples of our B matrix, so these beta parameters. So the missingness of each response variable is controlled by all the other variables as well. So it has an intercept term, but it's also controlled by the response variables and the predictors. But here I'm only showing the parameters for the response variables. So these intervals here, like many of them don't overlap with 0, which means like this beta 3 term could potentially be non-zero. And so we could argue that the data is missing not at random. And again, that's why our model is quite useful for picking up things like this. So we have a second model that differs slightly from the first model. So the first model, we're using PROBIT regression, and in PROBIT regression, we're assuming that the missingness has some sort of linear relationship with the data. But what if we want to model missingness with a more complex sort of relationship? That's where this second model comes in. So we still have a multivariate BART for the data, but now we have a multivariate PROBIT BART for the missing data indicator. So instead of this linear combination here, we have a sum of trees. And then again, we have a correlation matrix here. So there are a few reasons why I guess this model would be better than the first one. And something that I didn't mention is if you have missing data in the predictors, in PROBIT regression, you would have to first impute those values in your X matrix before you can run that. Whereas in this second model, there is a way to include missing values in the predictors without imputing it and running it with BART. But also the other difference, I guess, between this model and the previous one, you can still perform GIP sampling to get posterior samples of your position and so on. But the missing data itself cannot be updated via GIBs. You have to implement a Metropolis Hastings algorithm to get imputations. So this is a model that we're still working on right now, and hopefully it will work soon. But that's all I have for today. So these are some references, and thanks.
Thanks, Ailey. That was really interesting. Thank you.
Oh, thanks. Hello.
Thank you very much, YC. I guess we can ask, are there any questions? Yeah, well, I have a question. I just want to ask you about the missing values in the X's, YC.
Yeah, okay. Let me see if I can go back. So the missing values in the x's, I wasn't sure if I had time to explain that, but if I just use this as an example. So in these trees, you know, when we split the node, so here, like the first splitting rule is where x1 is less than 0.5. So if x1 is less than 0.5, then your observation goes to the left. If it's greater than 0.5, then it goes to the right. So if there are missing x's, there are 3 different ways of splitting that as well. So if, let's say, your splitting value is still this, like x1 less than 0.5, all the observations where x1 is equal to NA or like missing, you could split them to the left node or the right node with equal probability. There is also another way of splitting these missing values. So you could literally split on whether or not it's missing. So instead of x1 less than 0.5, you could split on x1 equal to NA. And then if x1 is equal to NA, they go to the left. If it's observed, then they go to the right. Does that make sense?
That makes perfect sense, Weisy. Thank you.
Thanks.
If we don't have any more questions, I guess we can start wrapping up. I guess. Thank you again for the talk, Weisy. It was great.
Thank you to you too.
I'll just step in from Maynooth University Library here. I'm Fiona, and just to say thanks very much to you, Conor, and to you, Yong Chen, for your talks this afternoon. We're really, really grateful for your participation in Love Data Week. And just to say, I think this is the end of our presentations for Love Data Week now. So I'm just going to post a link in the chat to where you will find recordings of the various sessions and the virtual exhibitions and other infographics from the week. If you haven't quite loved your data enough yet this week and you want to give it a bit more time tomorrow. So thanks so much to you both, and to everybody who's participated, and for everybody who's attended today. Thank you.